Hey folks, Mr. Dell here. This is the second part of looking at this problem, uh, number 106 from Math 1, from section 5.3.2. So I'm graphing currently. I'm graphing our values here. So let's see where I'm left off. I've got my 936, so 642. I need to graph that one, which is right there. And then last one is 245. So 245, which is halfway right there. All right, so there's my data. And if I look at this data, I can see it does look linear, right? And it is also decreasing, right? So we can see the slope. Not only when you talk about the slope, we also have to talk about its decreasing in this case, right? So now it wants me to describe. So I have my graph, and I can see it's going to be. This looks like a strong. I would say it's a strong. Let me rewrite that so it makes more sense. Strong linear association. Okay, so I'm going to say that's what we're dealing with. I don't see really any outliers. So I want to also find now it is linear. I did that. It is have a strong association. So what about its line of best fit? Right? Remember line of best fit, you're just to do that, you want to just find 2 points that kind of go through the middle of that data, right? So it looks like if I actually connect the first and the last point, I'm going to have a pretty decent line that goes through the data. So I can use those 2 points to find my line, my equation of my line, right? This first point here was 2 comma 46, and then this point here is the 9 comma 36. So I'm going to use those two to find my line, right? So the first thing is you find your slope, your change of y over your change of x. That's your slope, right? So remember, all lines are y equals mx plus b, m being the slope and b being that y-intercept or that initial value. So what we've got is I'm going to use those 2 points to find my slope. So my slope would be the change of y, which would be, in this case, going 46. I'm going to actually go 36, start with that point, minus 46 over, and then start with the same point, 9 minus 2. So if I see what I have a negative 10 over 7. So my slope would be negative 10 over 7. Um, and if we wanted to, we can put that as a decimal, just so that way we have some data here on what this really represents. So I might do that at some point. So when I interpret my slope, I can do that. But in my equation, I'll leave it as a fraction. So far I have my equation as y is equal to negative 10 over 7x plus some b value, right? And how to find that b value, remember, is what we've got to do is plug in one of these points into the x and y. So I'll go ahead and use this first point. I'm going to plug 46 into the y, and then I'm going to say negative 10 sevenths times 2 into the x, and then I do some math to solve for that b, right? So I have I'd have, this would be negative 27th when I multiply by 2 is equal to 46. So now I've just got to add plus b. So I add 27ths to both sides. So I really need to kind of determine here what I have just for the sake of keeping this in something that makes sense to me. That 27ths I'm going to call 2 and 6/7. So if I have 27ths, which is the same thing as 2 and 6/7, if I add those, I can see now that my B is going to be 48 and 6/7, so almost 49. So, and again, we're talking about a line of best fit. Since that's really close to 49, I'm going to go ahead and call that 49, just so I have a nice clean equation. So my equation here then is going to be y is equal to negative 10/7 x plus 49. So what does that mean? That means this would have crossed somewhere right about there, which makes sense at 49. So what does that equation entail? So let's interpret it, right? The slope, what is the slope? The slope tells me that negative 10 sevenths, and again, let's put that as far as in terms of a decimal, um, just so that way we can interpret it with this situation. So it's 1.43 approximately. So we're saying that 1.43, and the slope would be that the change of y, so the diameter, so it's 1.3 micrometers. Uh, the change of the length changes, the diameter changes. So for every 1 micrometer in the organelle, as far as the length, I get a change, I get an increase, or just give me a decrease in the diameter because we're dealing with it being negative. So it's negative 1.43 micrometers of diameter per micrometer of the length, right? That's the change. It's decreasing. So this is a decrease. It's decreasing in diameter. As the length increases, the diameter decreases. Okay. So that's what that line of best fit tells me. All right. And then one more thing we'll look here would be what would be the bounds for this, right? If we're dealing with truly a organism here, the organelle in tree saps, well, I would never have it be all the way to 0 in length, right? So it would never be a 0 in length because then it wouldn't exist. And it can only get so long before it doesn't exist at all. So you really kind of have these bounds of, so we'd say the bounds are from 0, and I'd use a parenthesis because it says it's not equal to 0. 0 to probably, if I think about where this thing is heading, because it's going to end up coming down to the x. When x is 0, you get for whatever when x is 0, your y is 49. So when y is 0, we'll be down here. So I wouldn't say it would get more than 10, 11. So just for the sake of this practical situation, I'm going to say no more than 12 or 11 as far as its diameter is concerned. So that might be the bounds based on what we have for our graph. So this is just in short here, the main thing was to be able to come up with this line of best fit and interpret what's really happening, seeing that there's a decrease in the diameter per increase in the length of the organelle. All right. Okay, there we go.